Hello, today we're going to be talking about the tree sorting algorithm. A tree sort is a comparison type based sort that places things into a binary search tree in order to sort them. In case you don't know what a binary search tree is, first you take your items that you're going to sort in an array, then you look at each one, the first one, you place that as the root. After that, you take the next subsequent values and compare them. If it's greater or equal to the root value, you go to the right and you carry that on until you find an open space. If it's to the left, if it's less than, you go to the left. And you carry this on like recursively until you find an open spot to place the value in your tree. Once you've placed all your values in your tree, you perform an in-order search in order to take them out and put them back in a new array. Once they're placed in this new array through the in-order search, they'll be in order. So that's how you do the search. Now let's talk about the properties of the tree sort. The tree sort has an average time complexity of n log n because placing items into a binary search tree has an average time of log n, and you have n items in your array. Now it has a worst case scenario of n squared, and this is because if your items are already in order, you're only going to have a single line, basically a list, and you're going to have to traverse every single item in that list to get to the end. So therefore, you can see that it's really bad if all your items are already sorted or mostly sorted. However, it's really good if things are pretty randomized. Some other properties of it is that the tree sort, it does maintain order. It is stable. If your first item is going to be a node and the subsequent node item that has the same value will be to the right. And when you traverse it, you'll get the first one back first and the second one back second. It also works okay offline because it moves from left to right. So therefore, it can keep taking new items being put in and just put them in the binary tree where they need to go. And it won't do the in-order sort until all the values are in. However, once it's performed the in-order traversal to resort new items, you're going to have to start the whole process over again. We talked about time complexity. We talked about when it's good, when it's bad. Some other properties of space complexity is O of n to store all the items. And let's see a demonstration. I am sorry for the angle that it's at. I couldn't find a better one to record it from. Just the light so you guys can see a little bit better. So today we're actually going to be sorting using the tree sort on Euro coins that I just found in my junk drawer. Here we have a 10-cent Euro coin, 5-cent, 50-cent, 2-cent, 1-cent, 2 euro, 1 euro, and 20-cent. Now we're going to perform a tree sort based on this. So we take the first value from the array, our 10-cent coin, and our tree's empty, so we place it at the root node. Now we move and take our 5-cent. We compare the 5-cent to the 10-cent, and the 5-cent is less, so it goes to the left. Now that spot is open, so we're going to place it there. And I'm just going to use these toothpicks so that once we add a bunch, it becomes clear what's root, what's node, and how things are going, rather than just kind of have them laying around on the table. Now we take our 50-cent Euro coin. All right, it is greater than the 10-cent, so we go to the right. Oh, that's an open spot, so we will place it there. Now we have our 2-cent Euro coin. We look at the 10-cent, it's less, go left. Now we see the 5-cent, it's left, it's less, so we go left. Oh, and we have an open spot, so we will insert it there. Now we look at our 1-cent Euro coin, same process, it's less than the 10, less than the 5, less than the 2. Goes to the left, and we have an open spot. Now we have our 2 euro coin. The 2 euro coin is greater than the 10-cent, so we move to the right. It's also greater than the 50-cent, so we again move to the right. Now we look at our 1 euro coin. the €1 coin is greater than the 10 cent, greater than the 50 cent, but less than the €2 coin. So it goes on the left. Just adjust this so it's clearer. Now we look at our last coin in the array. We have a 20-cent euro coin. We look at the 10 cent, it's greater. We look at the 50 cent, it's less. So therefore, it goes right there, to the left of the 20 cent, or left of the 50 cent. All right, so now we have our binary tree completed. Now it's time for us to do an in-order traversal. I didn't talk about the actual process earlier because it's easier to show. So for the in-order, we're going to start at the root and head left, down, left child, left child, left child, till we get to the end. This is the leftmost, so therefore it is the least. And then we're going to place it, I'm just going to demonstrate our sorted array. So the 1 value goes there in the sorted array. Now if we go up, we hit the 2 cent. It has no right or leftmost, like right to the leftmost, so 2 cent is next. Same with the 5. And the 10. Now that we've done this, we hit the 50 cent. We go to the leftmost, and there is a 20. So the 20 comes up, that goes away. We head up to this root. We take that, put that in. Then we head down again to the next left, go down to the right, and then as left as far as we can go. We reach the €1. So that goes into our sorted array. We go up to this root. We take this 2, and it has no right children. So therefore, we end the in-order traversal. And as you can see, it is in order. We have €1, 1 cent, 2 cent, 5 cent, 10 cent, 20 cent, 50 cent, €1, €2. And that's pretty much all that is to it. Thank you for watching.